A deceptively simple question, yet it is the key to understanding relativity. Is time universal? In other words, is there an audible tick-tock throughout the galaxy? The answer, my friends, is no. Time is not absolute. In fact, for us believing physicists, the distinction between the past, present, and future is but a stubborn illusion. Close your eyes. To truly grasp the idea of time, we must take a step back and ask, what is light? So, journey with me to the sun was Albert Einstein, right when he predicted that we would never be able to see the very beginning of our universe. For 100 years, the question has been at the back of every astronomer's mind. Now, the James Webb Space Telescope has peered back over 13 billion years into that primordial darkness using Einstein's own theories to do it, and it found, well, it found something that looked like emptiness. But what are we really seeing here? Is it really a void? And could this discovery of nothing actually be the most important discovery of all? It turns out the Webb telescope has found a shocking fact that both proves Einstein was a genius and at the same time challenges everything we thought we knew about how it all began, the universe we thought we knew. So to understand why finding this emptiness is so profound, we first need to remember what we expected to find. Our best scientific story, the Big Bang model, gave us a very specific picture of the early cosmos. For the first 380,000 years, the universe was an impossibly hot, dense soup of particles. Light was trapped, endlessly bouncing around. The entire universe was opaque, a cosmic fog thicker than anything we could imagine. Then, as the universe expanded and cooled, protons and electrons finally came together to form atoms. This event, called recombination, suddenly let light travel freely for the very first time. This is the oldest light we can see, the cosmic microwave background, but right after that first flash of light, the universe went dark. This is what scientists call the cosmic dark ages. There were no stars, no galaxies, just vast, silent clouds of hydrogen gas. This wasn't an empty universe. It was one full of a thick, light-absorbing fog. The established theory was that the first stars and galaxies would ignite slowly, like scattered embers. Their radiation would start to burn away the fog, creating little bubbles of transparency. Scientists believed this was a slow, uniform process. They expected to see a consistent foggy landscape with tiny galaxies struggling to burn through the haze. This was the timeline. We had the bedrock of modern cosmology. And this is precisely what the James Webb Space Telescope was built to test. Now, before we get to what Webb found in that darkness, we have to talk about how it was even possible to look. The light from the dawn of time has been traveling for over 13 billion years. And as the universe expanded, that light got stretched into the infrared spectrum. That's why Webb is an infrared telescope. But to see the absolute earliest corners of the cosmos, astronomers needed a trick. And that trick came from the very man who thought looking that far back was impossible, Einstein. Over a century ago, Einstein's theory of general relativity changed everything. He realized that massive objects don't just sit in space. They literally bend and warp the fabric of space-time around them. Think of a bowling ball on a trampoline. The heavy ball creates a dip, and marbles rolling nearby will have their paths curved. Well, Einstein realized that light must also follow these curves. This means a massive galaxy cluster can act as a giant natural magnifying glass. Light from a much more distant object passing by this cluster gets bent and magnified. It's called gravitational lensing. With its incredible sensitivity, Webb has captured images of this that are so perfect they almost look artificial. It's shown us Einstein rings, where light from a distant galaxy is warped into a near-perfect circle. These images are a direct visual confirmation of general relativity. We can see space-time bending. This isn't just a cool visual effect. It's the most important tool we have for studying the early universe. It lets Webb push past its own limits and peer into the era that was supposed to be hidden from us. Einstein, in his genius, had given us the key to unlock the very epoch he believed was sealed off. So, armed with Einstein's cosmic lens, astronomers pointed Webb toward the farthest reaches of time. They were looking for the faintest, reddest smudges of light from the first galaxies fighting against the cosmic fog, and they found one in particular tiny red dot called Jades-GS-Z13. We single quote, re-seeing this galaxy as it was just 330 million years after the Big Bang. This places it right in the middle of the era when the universe should have been almost entirely opaque. According to all our models, the light from a galaxy this young and small should have been swallowed up by the thick hydrogen fog around it. Seeing a specific type of light called Lyman alpha emission would be like trying to spot a tiny flashlight beam through a mile of dense fog. It just shouldn't be possible. But when the team analyzed the light from this galaxy, they saw it not a faint flicker, but a clear, bright signal. The flashlight was shining through the fog as if the fog wasn't. Even there was only one way to explain this. The galaxy must have already cleared out a massive region of space around itself. It had somehow punched a hole in the primordial hydrogen fog, creating a bubble of perfect transparency, and this bubble was enormous, estimated to be 2 million light-years across. For perspective, that's about the distance from our Milky Way to the Andromeda galaxy. This wasn't a small clearing. It was a vast cosmic oasis, an area of shocking emptiness carved out of the haze far earlier than any model had predicted. Webb had peered into the dawn of time and found a landscape that was being violently and rapidly transformed, full of massive, inexplicable holes in the fog. A universe being rapidly transformed. This one discovery has sent shockwaves through cosmology. It fundamentally challenges our timeline of how the universe evolved. The fact that this bubble of emptiness, or really transparency, exists so early creates what scientists are calling a photon budget crisis. Basically, to ionize a bubble that big, you need a certain amount of high-energy photons, a budget of light. The way we thought early galaxies formed simply doesn't produce enough photons that quickly. This has led scientists to wonder what were the very first stars really like. One idea is that they were true monsters, known as population 3 stars, hundreds of times more massive than our sun, burning incredibly hot and bright. These stellar behemoths could have produced enough radiation to punch these holes in the cosmic fog. Another, more exotic possibility is that the energy didn't come from stars at all. Some wonder if this galaxy already hosted a supermassive black hole at its center, blasting out colossal amounts of energy. Finding a black hole that big, that early, would be another massive puzzle for our theories. What this finding from Webb suggests is that the entire era of reionization, the transition from a dark, foggy universe to a clear one, may have happened much faster and ended hundreds of millions of years earlier than we thought. It wasn't a slow, gentle sunrise. It was a violent, patchy, and chaotic process driven by forces far more powerful than we had imagined. So, we come back to the paradox. How can Einstein be right if the universe Webb has revealed is so different from what we expected? This is the beautiful thing about science. These two discoveries aren't a contradiction. Einstein was right. His theory of general relativity and its prediction of gravitational lensing has been confirmed by Webb in stunning detail. Without his theory being correct, we couldn't have even built the tool, the cosmic magnifying glass, to see this far back. We couldn't have even asked the question. Webb's discovery of these pockets of emptiness doesn't invalidate Einstein. In fact, it's a new puzzle we can only investigate because of him. The emptiness isn't a lack of matter, it's a lack of the fog that we thought was everywhere. The discovery challenges our models of galaxy formation and the timeline of the early universe, not the fundamental physics of gravity that allowed us to see it in the first place. Einstein's theory is the solid bedrock. The surprising structure of the early universe is the new territory we can now explore because that bedrock is so solid. Einstein was right about how gravity works. And because he was right, we now know we were wrong about how quickly the universe lit up. The James Webb Space Telescope has opened a new window onto the cosmos. Through it, we've seen Einstein's century-old predictions proven right in stunning detail. And yet, we've also glimpsed a cosmic dawn that is chaotic, patchy, and evolving with a speed that defies our models. The discovery of these vast bubbles of transparency has shown us that the first galaxies were not timid sparks in the dark, but cosmic engines of immense power that reshaped their environment with a ferocity we are still struggling to explain. And the deeper Webb looks, the more questions it uncovers. What truly powered these first galaxies? Were they filled with monstrous stars or born around primordial black holes? What does this rapid, violent transformation tell us about our own cosmic origins? These are the questions that will drive astronomy. For the next generation, we thought we were searching for the edge of the universe, but instead we found the edge of our own understanding. The journey into that beautiful confusion is just beginning. The universe is constantly revealing new secrets, and each discovery leads to even more profound questions.